Hello, chemistry students. This is your professor, Sean McMahon. And in this lecture, I'll be covering chapter 2, which essentially covers the early topics of the scientific method and your math review. The second portion of this chapter that I will also be covering in another video will then go using our math review to determine measurements, use them in calculations using conversion factors, and also learning a little bit about problem solving and density. So let's go ahead and get straight into the actual lecture. So chemistry, why are we studying chem? Well, it basically, what it tries to do is explain everything we see, because everywhere we look, it's basically made of chemicals. I like to tell students, basically chemistry is the study of matter. Matter is anything that takes up size and space, and we're studying how matter can undergo chemical and physical changes, and during those chemical and physical changes, we might see changes in energy and state changes as well. So going from, for example, a solid to a liquid to a gas. So how is chemistry involved in this picture that we're looking at? Well, again, everything's composed of atoms, so all matter. They can combine and form mixtures, okay, like the soda pop. The shapes of the molecules and the properties of the molecules and atoms determine its flavor, color. And the fizz is an example of a phase change, something going into a gaseous state, and that is determined, in this case, based on the solubility and the pressure above the soda pop. And of course, there's the temperature aspect in this picture as well. So temperature, we'll see, is directly proportioned based on molecular motion. So the faster molecules are moving, the hotter things are. And we measure heat energy using a temperature scale. So the first thing is, to be a chemist, we want to know a little bit about the scientific method. Many of you have probably already learned about this in biology, but basically it's a way of emphasizing observations and using experimentation to help us understand the world. Okay, so it first was brought upon by the philosopher Aristotle. So basically there's several steps in the scientific method. Typically you question an observation. So maybe you're out in nature and you observe some type of event that occurs. Based on that event, you try to draw some type of explanation or a hypothesis. So you construct this crude explanation, and then you're going to design an experiment so that you can test your hypothesis to see whether or not it's a decent explanation. After you test your hypothesis, you're basically going to analyze your results. Now, your results in your experiment can be both qualitative and quantitative. Again, with chemistry, it's a physical science. It tends to be more quantitative, which means it's going to involve numbers. Once we analyze the results, we're going to be able to form some type of conclusion. A very easy way to memorize this is, I call it the OHEC method. OHEC. I have to learn science. It's really difficult. The O stands for observation. The HEC stands for, or the H stands for hypothesis. The E stands for your experimentation. And again, that could be qualitative, right? Or quantitative, right? So your data that you collect can be either one of these. So qualitative might be where you take two solutions, you combine them, and there's a color change. So you would describe the color change. Maybe if there was a temperature change, that's all qualitative. A quantitative form of data would be, you actually measure the temperature change in the test tube once you combine the two solutions. Or maybe in a qualitative experiment, you combine two solutions in a precipitate form. So basically that's a solid. Well, to make it quantitative, you can filter the solid out, dry it, and then weigh it and figure out its mass measurement. So those are all examples of experiment and the different forms of data or results that we can analyze. Now your conclusions there's basically two types of conclusions. There's laws and theories. So a law pretty much explains what is going to happen. So what happened, and you can't argue it. This happened. This physically happened. So I can't argue that if I let go of that pen, what's going to happen is it's going to drop down to the ground because of gravity. The theory is why it happens. So when we discuss, let's say, nuclear chemistry, and we're talking about the location of electrons, we can explain why they're located at certain distances and energy levels based on the number of protons and the number of electrons, okay? So again, a hypothesis. We're trying to explain some phenomenon that we've seen in nature. Theory is a well-established hypothesis. Basically, it's an explanation, and it has considerable evidence that supports it. So basically, you have to do numerous experiments for it to succeed, this theory, and other people have to be able to conduct the same type of experiments and get the same results. Theories are kind of difficult. A law, basically, there's no exception. Under natural conditions, it's just going to happen. You may not know why it happens, because again, the theory is why. The law is what. Okay. So if you're testing a law, you may not know why it happens, but you're testing to see, does it happen under all these conditions? And if it does, then that's supporting that it's a law. However, Einstein says no amount of experimentation can ever prove me right. Right? So you can have endless amounts of experimentation to finally get to these theories, and then later in time, they're proven false. And we'll see that when we talk about atomic structure, that, you know, there's all these preliminary elementary procedures, and as time goes on, you know, they kind of get canceled out. But one experiment can prove you wrong. In fact, in a lot of sciences, you create what's called a null hypothesis. And the null hypothesis is actually the hypothesis that you're trying to disprove in the experiment, because it only takes one experiment to disprove something. So you can cancel out the null hypothesis to support your true, right, hypothesis, your alternative hypothesis. It's fun stuff. So in science, because we have to have the scientific method, right? We have to conduct experiments and collect data, right? We have to answer questions. And we're kind of biased. Numerical values tend to be the best to answer a lot of these questions. So here's an example. The question might be, what is the mass of this blue solid sample? So you're going to write a number. Now, there's a problem there. What's wrong with this number? Well, is it 1.2 inches? Is it 1.2, I don't know, feet? What is it? So in all of your measurements, you can't just have a number. So that is a difference between math and science. You have to have a unit. The unit means everything. So if I told you I was 188, what does that mean? IQ? I wish. Does it mean pounds? I'm 188 pounds. I wish that too. That's not the case. Or could it mean 188 decagrams of cholesterol per deciliter of blood? That's a possibility, but I won't know unless I include that unit. And that's why you always have to have a unit. Now, in some cases, we have measurements that are numbers. Those tend to have some, you know, round off possible errors because we have to make a prediction and no one's perfect, okay? Or we have exact numbers, which are a little bit easier. Now, exact numbers are things you can count. So there's no discrepancy. It's not really an inexact number because you can know the number of items. So a really common one is a dozen. Dozen eggs, 12 eggs. A week, there's 7 days. A dollar, there's 100 pennies. A kilometer, there's 1,000 meters. 7 quarters. Okay, so these are considered exact numbers. You can count them, right? I can physically count those 7 quarters. So that's treated as exact. There is no uncertainty. There is no doubt. So some are inexact because you have to approximate. There's a level of uncertainty. So for example, a temperature measurement, there's some level of uncertainty. The mass of a person, right? Have you ever been on a scale and it kind of fluctuates because of wind currents, or maybe your pressure on the scale changes and shifts a little bit? So because there is some uncertainty, some level of doubt, dependent on the instrument's precision, we call that an inexact number, okay? I just say there's some, it's a doubtful number. There's some level of doubt. So again, all these measurements. So if I'm to look at this, and this will tie into, for those of you who have the sample questions to go along with my lectures, this would be sample exercise number 1 in the PDF. And for the first part A, 38.15 centimeters. Is that exact, or is that a measured number? Well, it's a measured number. You had to take a ruler, use the lines, the graduations are called, to make a measurement. So because of that, it's inexact because there's going to be some level of uncertainty at one point. You have to estimate somewhere. How about 15 pencils? Could I count 15 pencils and by no doubt there be 15 pencils? Yes, because I can count those out. That's treated as exact. $1 to 100 pennies, that's an exact. There's no doubt there, no level of uncertainty. So that's sample exercise 1, and that helps us understand the difference between exact and measured numbers. And again, why are we doing this? Well, in chemistry, we have to take measurements, right? Because we're following the scientific method. We're trying to explain observations, developing hypotheses to come to conclusions. Now, when we're taking measurements, there's 2 terms you have to be comfortable with. 1, accuracy. 2, precision. So the accuracy is how close you are to the true value. You know, did you hit the nail on the head? Did you get it right? Right? Precision is basically more geared towards your technique. Are you consistent? Right? So are all your measurements close to one another because you have a consistent technique? And in lab, when you're performing experiments, you want to be precise. Okay, the more precise you are, typically that's going to help pull you over to accuracy, because if you have a consistent technique, if you're off in accuracy, you can adjust your technique to make yourself more accurate. But if you're inconsistent with your technique and you're all over the place, you'll pretty much never, I mean, it's much harder to be accurate. So accurate means correct, precision means consistency. So I always like using the example of a dartboard, okay? So you have a couple examples here, okay? 4 dartboards. I know it's weird, A's down here, okay? But we'll try to match the numbers with the letters, okay? Based on the figures, right? So which of these, A through D, is accurate and precise? Well, if you ever play darts, you know, the whole goal is to get it in the bullseye. And this person is amazing because they're getting them all in the bullseye. That's kind of rare. What about accurate but imprecise? So that would be B. Now, why is that? They're not consistent with their throws. However, one of the things you can do, right, for this type of error, this systematic error, is, and systematic error, a lot of people say that's human error, okay? What systematic error is, you need to, you know, fix the technique. Actually, I'm sorry, this could be caused by random error fluctuations in the room and things like that. So random error is a little bit different. That has to do with air fluctuations, you know, the pressure in the room. But in this case with the darts, you know, maybe there was something that caused it to sway. The good thing to do to fix the random error is take an average and do multiple trials. So the reason why this is accurate, even though it's not consistent, is I'm doing multiple throws, and on average, it's somewhere in the middle. So that takes care of randomness, okay? Inaccurate and precise, I'm sorry, that's what I was talking about earlier, we see and see. So this person is very consistent with their throw, right? But the systematic error is they're off a little bit. So all they would need to do is step over to the right, and then when they use that same technique, because they're precise and consistent, they would fix their accuracy. So that's systematic error. Another example of a systematic error is a scale that's not calibrated correctly. So when you weigh it, it's always off by 0.1 grams, or using a ruler that has a chip on the end. So even if you're consistent with your measurement, you're going to be inaccurate, right? Because of that systematic error. How do you fix systematic error? Calibrate your scale, get a new ruler, or in the case of the dartboard, adjust a little bit to the right. So the last is inaccurate and imprecise. And this is what you don't want to be. I mean, I hate to say that. You just don't want to be that situation, because it's kind of, yeah. Even if you average out the random error, you're not going to be accurate. And because you're inconsistent, you won't be able to adjust your technique as well. Here's another example using a bar graph. This is because we like to present our results and analyze our results. So how do we present data? How do we analyze our data? A lot of times we use graphs, right? So here's, your typical bar graph, and it's showing here that student A, right? They're kind of all over the place. They're inaccurate and imprecise. So they lack precision, right? Because they're all over the place, and they're not accurate because their average is off. Well, if we look at this individual, student B, they're precise. You see, it's very consistent from their average, right? But it's not accurate. It's a little bit off. And then you get the student that covers both, right? So they're consistent and they're right on the money. This student, much easier. Student B is better off than student A because they can make adjustments to get the accuracy. So precision in lab is the first thing you want to do. So how do you become precise? Well, one of the things is you want to minimize, in your measurements, error. And one of the things to do that is to make sure you know how to read your instrument, right? Because again, there's always some uncertainty. There's always going to be some level of doubt. So the more precise the instrument is, right, the less error you're going to have. So errors in measurements is typically indicated by what's called significant figures in the number. So what do I mean? So let's take a measurement here. So here I have a thermometer, okay, and it goes all the way down. I just didn't want to put the whole thing on here. And I know it's a thermometer because there's the unit F, and you see that little degree symbol, that means Fahrenheit. So this is in Fahrenheit, which we use in the United States, okay, which that's a whole other topic, but pretty much everybody else uses Celsius. But when we go into the hot tub, we notice that, okay, this large graduation right here is 100. This large graduation is 110. Between 100 and 110, there are 10 graduations. So that means if there's 10 graduations and I divide them, because the range between, to get a range, I take my max value or my high value and I subtract my low value. The range is 10. So there's 10 Fahrenheit between these 10 graduations. That means each graduation is 1 degree Fahrenheit. Now, why am I doing that? I need to figure out what each mark is, because that tells me the precision. You can think of precision as the placement value of your measurement. What placement value are you? That's what precision basically is. So when I look at my measurement right here, it looks like it's between two numbers. So if this is 100 and each graduation is 1, this is 101, 102, 103, and 104. So my measurement's between 103 and 104. So there's no doubt there. I know for sure that this temperature is above 103, but is less than 104. So where is there the uncertainty? I have to guess in between 103 and 104 to the 10th place what that measurement is. And I can do that. It's an educated guess, right? I can estimate that with my naked eye, right? And what I end up getting, sorry about that, is I estimated at 103.4. So what does that mean? Because each graduation is to the ones place, my estimate is to the tenths. I was going to write 10, but really what I should be doing is writing tenths. Sorry about that. Now, because there's a level of uncertainty at the 10th place, why? Because the graduation's at their 1. A lot of times you'll see afterwards plus or minus 0.1 degree Fahrenheit to show that there is a little bit, you know, really this measurement could be 103.3 or 103.5. So that's why a lot of times you see that level of uncertainty, the plus or minus symbol followed by a number in measurements. So when you report measurements, we have to, you know, we want to write all the numbers, okay? And when we write all those numbers, like we did with the 103.4, right, we're going to call those significant figures because all these numbers are significant in our measurement, okay? So what does that mean? Our measurement had 4 sig figs. Why? There's 4 numbers here, all the way to the tenths. So I have the hundreds, the tens, the ones, and the tenths. That's 4 digits, 4 significant figures. So when we're writing our measurements, all the digits need to be written with certainty. And then the last one is typically your estimate. So if this was a measurement, right, the ones in red are for certain. And that last digit is where that estimate took place, just like I did here. And that would be the doubtful digit. Okay, but we would write all of this. And if I look, how many sig figs are here? Well, there's 1, 2, 3, 4, 5. This would be 5 sig figs. Sorry, sig figs is significant figures for short. So there's 5 significant figures here in this measurement. What is this measurement missing? A unit. So when we're recording significant figures, we got to take this into account, and not all the instruments are going to have the same markings. So we have to be able to look at the markings and determine what they are, right? And just remember, between the markings, when your measurement lies between, right? So with the thermometer, between 103 and 104, that last digit that is significant has a level of uncertainty. That's okay. We're still going to record it. Okay. So sig figs only apply when we're determining significant figures to measurements, not exact numbers, right? So when I said a dozen is 12, there is no number of significant digits because it's an exact number. It's like saying 12.000 for infinity. There's no doubt. Okay, so this is only when we're doing measurements in lab. Okay, so here's an example. I have a ruler. Rulers measure length. The unit for length in this ruler is centimeter. Okay, I know here in the States we use inches, but you flipped it to the metric side where we have centimeters. Okay, and I'm measuring this solid here. And now when I look, I see it's between 4 and 5. So without doubt, it's more than 4, but less than 5. So what do I have to do? I have to make an estimate. Where do I go? I go, if my numbers, my graduations that are labeled are to the ones, I go 1 to the right, and that's the tenths. So I might say this is 4.2. Why? Well, that looks about a 0.2 if I was to divide this into tenths. What do I also see? I see a plus or minus 0.1 centimeters. That's saying that there's a level of uncertainty. It might be 4.1, it might be 4.3, but I'm saying it's 4.2. Okay. Now, with this next ruler, it's still measuring 10 centimeters. However, the ruler has greater precision. Why does the ruler have greater precision? Because now, if I notice between the 4 and the 5, there's 10 graduations, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if the difference between 5, right? Because remember, I have to take the difference. 5 minus 4 centimeters is 1 centimeter. And there's 10 graduations. So that means each graduation must be 0.1 centimeter. Okay. So now, when I look at this, I might say to myself, oh, it's between 4.2 centimeters and 4.3. You can see that right there because there's 4.1, 4.2, 4.3. So I'm more precise. I go to a greater placement value. So because the graduations are to the tenths, my estimate goes 1 over and it goes to the hundredths. So I might say, okay, this measurement, right? It's between it's greater than 4.2, but less than 4.3. I'm saying it's 4.2. The graduations are to the tenths. I go 1 over to the hundredths, it's 4.25. But again, because I have an estimate, I see plus or minus. I don't see 0.1, right? That level of uncertainty didn't take place at the tenths because the graduations are the tenths, and there's no doubt there. The uncertainty goes to the 100ths this time because that's where I had to estimate. So how many sig figs do I have here? Well, I have 1, 2, 3. I have 3 significant figures in my measurement. I count all of them and I record all of them. So ruler A, there was only 2 sig figs, and it only went to the tenths because the graduations were the ones. Ruler B, there was 3 sig figs. So what does that mean? It's more precise. Why? Because its graduations went to the tenths, so my estimate was to the hundredths. So being more precise is going to lead to better accuracy, and it's going to make me more consistent with my measurements. So ruler A has more uncertainty. I only go to the tenths. It's not as precise, right? Ruler B goes to the hundredths. So ruler B gives me more precision. I want to use that for my measurements. So what about this one? Right? So when I look, this is only going to the ones. So at most, I can only go where? To the tens. So I might say for this, I don't know, what is that? Looks like 2.2 centimeters. Of course, I could write this. Yeah, for me, you don't have to. Some profs might make you. But basically, it's 2.2 centimeters. It's understood that, you know, at the 10th place, in this case, there's some level of uncertainty. What about here? I measure the same paperclip. Look at that. I was a little bit off, right? If I look, this is why it's better to use a precise instrument. I see that this is 2.1, 2.2. It's between 2.2 and 2.3. Now, my gosh, it looks like it's right on 2.3. So it's on 2.3, but because I can go 1 over, because it could have been, instead of on the 3, the 0.3, it could have been between 2.2 and 2.3, and I would have went 2.25. But because it's right on, I still have to show the level of precision of that instrument. So what does that mean? Well, I got to add a 0 in the hundredths place to show that my measurement is actually to the hundredths. Now, I know that can be hard for some people, but basically I'm adding that 0 to show the precision of this ruler. This ruler goes to the tenths, so I should be able to read to the hundredths. If I just write this, it appears that I'm using this ruler here that only went to the ones, and my estimate was to the tenths. But this ruler is using, this ruler here is using tenths, so I should be able to go to the hundredths. So I add that 0 to show that. Now, someone might go, man, I don't know if I want to do that because I know there's some level of uncertainty here to the hundredths. I might just do 2.29 centimeters. That's okay. You can do that too. I just wanted to tell you that sometimes you will have to add a 0 to your measurement to show its precision. Okay. Now, here we get to see the precision, right? I got 3 volumetric pieces of glassware. Now, beakers you never use for volumetric measurements. They're typically used to carry things, from the stock solution to your worktop, right? Because you don't want to take the giant stock jar and pour it at your bench top when you're in lab. You pour the small amount, carry. So usually beakers are used for transport and things like that. But what it's showing here, right? The beaker is calibrated by 10 milliliters, right? So I'm at the tens place. So when I do this measurement, it's going to be kind of gross. My, measurement can go to, I guess, the ones, right? If I go to the ones, I might say, oh, this is like 28 milliliters. That's all I can do, right? Plus or minus 1 milliliter. Now, a graduated cylinder, it's a little bit better. The graduations, right, between 10, right, unlike here, if I look right here, there's only one graduation between 10 mils. So the graduations are 10. Here, typically they use, in this example, it would be 1, 2, 3, 4, 5. Typically you have 10 graduations, so you could go to the tenths, okay? Over here, between 1 mil, your graduations, there are 10, so you can go to the hundredths. Let's do a couple examples to make better sense of that. So in this volumetric measuring device, we have 20. Here we have 30. Okay. So between 20 and 30, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10. So each graduation, right? This would be 21, 20. Each graduation's to the ones. I should be able to go to the tenths. Okay. I know it's a little bit more than 21, a little less than 22. What do I get? I go to the tenths. I say it's 21.2. Oh, it's a thermometer. 21.2 degrees Celsius. Okay. The 2 has got a little of uncertainty. There's 3 significant figures because there's 3 numbers. Now with this measurement, same thing. 21, 22, but now it's right on that 22 graduation, right? But remember, because the graduations are to the ones, I should be able to do my measurement to the tenths. So what do I do here? I add that trailing 0 at the tenths. And that last 0, there's a little bit of doubt there, but I still record it because I want to show that this measurement is to the tenths because each graduation is to the ones. So it's 22.0. And it's 3 significant figures because it's to the tenths. Now, this last one, I notice that this is 21, this is 22, but each of these graduations is 0.1. So I should be able to go to the hundredths. This is 22.11. It's just above the 22.1. It's between 22.1 and 22.2. 2. And in this case, there's 4 significant figures. 1, 2, 3, 4. So with sig figs, if you're in lab, you can use the device's precision to help you determine, its level of precision, right? So you can use the graduations. What if you're at home and you're looking at a problem in a book, like a homework problem, and you didn't really take the measurement, but they're just giving you numbers? How can you determine the sig figs? Or there's rules for that, okay? So the first rule, and I give them, weird names, but for the first rule, it's all non-zero digits are considered significant. So the digits 1 through 9, if I write them in a homework problem online, your book, means it's significant. So if I see the number 12, how many non-zero digits are there? Well, there's 1, that's 1 non-zero digit, and there's 2. There's another non-zero digit. So there's 2 sig figs because there's 2 digits. Where does it get difficult? The zeros, right? Why? Because there's pretty much 3 different types, and they're tricky for students. So I'm going to give them, like I said, goofy little names to help you memorize. So the first one I called the captive zero. The captive zero is held between non-zero digits, okay? And they always count as significant. So you may remember we wrote 103.4 degrees Fahrenheit. Remember when we use the thermometer? This 0 right here is captive. Why? It's held between the 1 and the 3. So it's between 2 non-zero digits. So it always counts. And you might remember we said that this was 4 sig figs. Okay. So what would 102 be? Well, you have 2 non-zero digits. The 1 and the 2 are non-zero digits, but the 0 in between them counts. Why? It's held captive. And that means that that measurement went to the 1's place. Okay. So I'm going to write 3 sig figs. Leading zeros. Now, leading zeros, they're always to the left of the numbers, and they're used for placement value. Okay. So we don't count them as significant. They're just to put things in the right place. So if I look, all these zeros are to the left of non-zero digits. So what do? Just cross them out. They're not significant. They're just putting the 5 in its proper place. So in this, it's tenths, hundredths, 10,000ths place where it needs to be, okay? But those zeros, they don't count as digits, and the significant digits. There's no numbers there. So this would only be 2 sig figs. So leading zeros, right, are not significant, and they're always to the left. And you can remember left because lift up your left hand and make an L. So rules for sig figs continued. The zeros that are hard are the ones to the right of numbers. And they're referred to as trailing because they're trailing behind. Why is it difficult? Really, there's 2 types. A lot of books refer to as the ambiguous case. This isn't really ambiguous because if you look at it in terms of the decimal placement, there's no ambiguity. You know exactly whether it's significant or not. And what do I mean by that? Well, if there's a decimal point, you're telling me right off the bat that there's significance. Okay. So that's important. One example, I think it was, we did the 4.30 centimeters I wrote earlier. I'm putting that 0 there because that ruler, if you remember ruler B, it had the graduations to the tenths. So I was able to estimate to the hundredths, but it was on that, 4.3 graduation, but I still added the 0 because the instrument can go to the zeros or to the hundredths place. So they always count if there's a decimal. So in this case, Again, the ones to the left, this is why it's tricky for people. These don't count. Okay. This one does because it's going to that placement. I'm following it. It's trailing. So in this case, I have 3 sig figs. Now, if you're having problems with that, you can kind of go back, record, or pause, look at the recording. I'm going to keep going because sometimes they don't count. So in the example of 10,000, like if I had an arena and it fit, 20,000 people, and I look around, I'm like, there's about half people, there's about 10,000. It's not very precise. So, these zeros to the right, there's no decimal. See, when there's not a decimal, they don't count because I don't have any level of precision like I did with this instrument. So in this case, these trailing zeros, there'd only be 1 sig fig. So the key, if there's a decimal point, it counts. Without a decimal, doesn't count. That's the key. Chicken scratch, sorry about that. I'm actually writing face up instead of down, but okay. So counting sig figs, you want to count all the numbers. So leading zeros don't count. Trailing zeros without a decimal don't count. So we're always counting the numbers. So here, there's 2 sig figs. These don't count because leading never. This is 2 sig figs. Why? It's trailing, and sometimes they count, but in this time, they don't because there's no decimal. So let's take a crack at it. Number 1, 0.98, right? This is leading. The 0 doesn't count. 2 sig figs. 0.0405. Now, there's 2 types of zeros here. I have leading that never count. Remember, to the left, cross them out. But what is this? It's the captive. It's held trapped between 2 non-zero digits, 3 sig figs. Now, these are trailing because they're to the right. But remember, there's 2 types, with the decimal and without the decimal. This is without. So there's, they're not telling you it's the precision of the ones. So how many sig figs here? 3 sig figs. Again, there's no ambiguity because really to have more, you would put a decimal here or here. So in this case, 9.90, 3 sig figs. Why? There's a decimal and trailing zeros with a decimal count. So how many significant figures? So if you have a practice problem, hopefully you use this. And now you can look at these numbers on that handout for chapter 2, exercise number 2, and determine the number of sig figs, right? So how many sig figs? Well, 1, 2, 3, 4, 5. They all count 5 sig figs. What about here? Leading never count. These are captive, they count. These are trailing, they count. Why? Because there's a decimal. Even though it's way over here, there's still a decimal present. So those trailing count. So how many? 1, 2, 3, 4, 5, 6 sig figs. Here, this is trailing, there's no decimal. 2 sig figs. This is trailing, but now someone put a decimal. So what does that mean? They count. 4 sig figs. Oh, I went out of order. I'm sorry about that. Reading left to right here. C, how many sig figs? Well, this is captive because it's held between these 2, and this is trailing, but there's a decimal, so they all count. 1, 2, 3, 4, 5, 6, 7. 7 sig figs. Decimal, so these trailing count. 1, 2, 3, 4 sig figs. Leading never count, just put a line. 3 sig figs. I want to make it easy on myself. Right? And then over here, what do I have? Leading doesn't count. 1, 2, 3. This counts because it's captive. 4, 5, 6 sig figs. Okay, so that's sample exercise 2. Now, sometimes when we do calculations, right, even if we don't have the measurements to help guide us with precision, we could use our sig fig rules like we just did, but we might need to round a number. You may remember this, in math, they'll say round to the tenths. It's not always going to be the tenths, right? Instead, it might say round to where there's 4 sig figs or 3. Okay. So when you round, you always look at the last digit, right, being dropped. So all the other digits you don't look at, right? So if it's a 4, the last digit, right, before being dropped is a 4 or less, you just drop everything. If it's 5, then where you're rounding, you round up. So an example, if I was rounding this to the tenths place, this is what they do in math. We're not going to do this really, but in math, if you were going to the tenths, that's right here. This is a 4. So what does that mean? All right, I go to the last digit being dropped. I don't look at the 9. I only look at the 4. It's a 4. So I just drop all this and I'm left with the 2.3. I know that's really easy for you, but I like reviewing it. Now, sometimes you're going to be performing calculations and you're going to have operations, and the operations have different rounding. That's part of the reason why I'm going over this, okay? So in a calculator, you may need to round to 3 significant figures. So whatever comes up, it doesn't matter if that third sig fig is in the tenths, hundreds, thousands, it doesn't matter. You still, your answer, and we'll go over these rules in a moment, you need 3. So what do? I go 1, 2, 3. And what do I notice? Right? Right before I drop where that third sig fig is, there's a 4. Because it's 4 or less, I'm just going to drop everything and I'm left with 12.8. Now, if my calculator displayed this and I want 3 sig figs, I go 1 to the right of where the 3 sig figs are, and now I see a 5. So what am I going to do? When I dropped all this, I just left it because it was 4 or less. When I drop all this, because this is a 5, I need to round up, and that's why I get 12.9. Again, what's wrong with all these numbers? There's no unit. So in chem and physics, there's going to be a unit, and bio, there's going to be a unit, okay? So but right now, this is math review. So we're bridging what you've learned in math to apply to measurements in the physical sciences and chemistry and life sciences. So remember, we talked about placeholders, right? Adding a 0. So round the measurement to 2 sig figs. So if I have 151 milliliters, this is a really common mistake, is students will say, oh, 1, 2, I'm 15 mils. No. Right? If I'm measuring 151 mils and you put the answer 15 mils, that's like a tenth, right? It's like if I owed you $150 and I just gave you 15, you'd be a little upset, right? So if you want 2 digits, what we're going to do is we look here and we got to drop it. I don't want to just drop it and leave it at 15. I have to add a 0 as a placeholder. Now, why does this 0 not count? It's trailing without a decimal. So now it's just being used as a placeholder and it's not significant. What if I want 2 significant digits here? I go 1, 2. So I'm going to drop this. Again, am I going to do 27? Or actually, I would round up 28. No, that's going to upset people. All right. If I owed you $2,788 and I gave you 28, you'd be upset. I know I would. So what would be better? What do I need to add? Placeholders. So it's 2,800. And look, I'm starting to use units. Oh, yeah. Right? 2,800 grams. So you might have to round some numbers. So like this, I need to round 2. So what do? These are leading. They never count. I go here, 1, 2. That's a 9. I'm going to drop it, but I need to round up. So my answer is 0.064. Okay. What about here? 1 sig fig. Whoops, I went a little crazy with my underline. Right there. Am I going to drop everything and put a 2? No. What do I need? The zeros as placeholders, because I only want 1 sig fig. 200. Looks like I forgot that. What about this? 3 sig figs. 1, 2, 3. Uh-oh. This is tricky, right? Because I got to round up, but that's going to bring that to a 0, and that's a 6. So if I go 4, 6, because that's going to bring that to 60 instead of 59, and then I would add the 2 zeros, that there's a problem there. Those trailing zeros, they don't what? They don't count. There's no decimal. Now, if I go like this, that's not 3 sig figs anymore. This would be 1, 2, 3, 4, 5 sig figs. So what do? Some of you know this already. You use scientific notation, right? So exponential notation. I could say it's 4.60. I add the 0 as a placeholder to show that the precision is to the 3rd sig fig, which is right there. But when I do it in non-scientific notation, I can't use a decimal. When I use scientific notation, boom, now I can use a decimal. It's 4.60. And I can go times 10 to the, so I'm going to move the decimal over how many times? 1, 2, 3, 4 times 10 to the 4th. And I know that basically, you guys know this. I'm going to review this in a minute. But basically with scientific notation, you always move the decimal after the first non-zero digit. The first non-zero digit is 4. This number is bigger than 1, so my exponent is positive. Okay, same thing here. I want 2 sig figs. So I need to go here. I would drop that, but if I write 200, and I'm back over here. So I need to employ decimal, but if I do this, that's 3 sig figs. So what do I use? Scientific notation. I go 2 after the first non-zero digit, I put decimal, and then I add the 0 to get that 2nd sig fig. And then I move this over 1, 2 times 10 to the 2. Why? Because this number is greater than 1. So there's 2 sig figs, and I go 2.0 times 10 to the 2. Now, why am I showing scientific notation? Why am I showing rounding? Why am I showing, okay, in some cases, they're not going to say round to the 10th. It's just going to be 3 or 4 or 2 sig figs like we just did. Well, because when you get the numbers, you're going to crunch the numbers by doing operations. So most of the calculations we're going to be doing in this class are multiplying and dividing. That's like the bulk, almost all of it. It's multiplying and dividing. So when we multiply and divide, what we do is we look at the number with the least number of significant figures. So if I count here, there's 4 sig figs, and there's 3 sig figs. And I'm multiplying them. So what is less, 3 or 4? 3. So my final answer should have 3 sig figs. If I am paying attention to rounding, I go 1 to the right of the last significant figure, the 4, because there's 3. I see that this number is less than 4 or 4. I drop that whole thing. I don't round up. And I get 324. And what's beautiful, I don't forget meters. And remember, meter times meter is not meter. It's meter squared, okay? Because it's like saying x times x, that's x squared, right? The only time that would remain as an x is if you had x plus x, then that would be 2x, right? So then you would leave the x, but this is multiplication. So now that is a squared value, like in the case of an area, right? So this is representing an area. Length times width. So maybe this was the length and this was the width of this, you know, I don't know, rectangle. So the squared area was 324 meters squared. Area, because it's length times width, is always squared, right? So it's a unit, whatever that unit is, squared. We'll see that volume, which is length times width times height, will be a unit to the third power, because volume, right? Here's a cube, you know, if you had a centimeter, 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 you times that, it'd be centimeter cubed. It's a cubed value. All right, enough of that, Sean. Let's go into exercise 3, where we're going to apply these rules. So, how many sig figs? 4. How many here? Leading, don't count. There's 3. So 3 sig figs. I underlined 3 sig figs. Why not here? Leading, never count. I see this 2. It's not 5 or greater, so I'm just going to drop it. Boom. There's my final answer. Right? And it's centimeters squared. Why? Centimeter times centimeter. And why are we including the unit? Because without the unit, the number doesn't mean anything. We're not in math anymore. Chem. We're taking measurements. This is a length measurement, length times width. This is an area measurement, right? Maybe you have to measure out a piece of aluminum foil to determine its density, okay? Here's division. We follow the same rules, right? We're going to pick the least sig figs. So how many sig figs here? Well, 1, 2, captive counts. So that's 3, 4. Trailing counts because it's decimal. So there's 1, 2, 3, 4, 5 sig figs. And how many here? 2 sig figs. Why? This trailing doesn't count because there's no decimal. If there was a decimal right there, then it would count, but there isn't. Okay, so in this sample exercise number B, we want 2 sig figs. So what did I do? Leading, never count. I underlined 2 sig figs, stop at the 4. Oh, that's a 7. So I round up 0.15. The unit, gram per mil. Why? Grams divided by milliliter. We're not going to use the slant for fractions. You'll see that backslash like that. We will not be using that because when we go to dimensional analysis and conversion factors, it helps us much better to do it in a linear fashion to show our units in our quotients. I call this a quotient because this is a numerator, this is a denominator. It's a ratio. Here we go again. So we got how many here? 3 sig figs, 1 sig fig, right? Because those don't count. So I can only have 1 sig fig. I underline the 1. Oh, it's a 5. Yup. Believe it or not, you're going to round it all the way up to 0.2, right? Because you only have a confidence of 1 sig fig here. Yeah, I know. Now here we have multiple, right? Basically, if you look, this has 2 sig figs because leading don't count. This trailing does. This has 3. This has 3 because captive leading never counts. These leadings don't, so 2. So basically, the smallest amount is 2 sig figs. Okay, so your final answer should have 2 sig figs. But how are we going to punch it in to our calculators, right? So this is a TI 30X that I asked you to buy. It's a $10 calculator. So I'm going to show you on this calculator how you plug it in. It works for other ones too. Do it 2 ways. Yours might not look like this, but if you look at the TIs, they typically have this EE button over the X squared, and you have to hit the second function first, okay, to get to it. But the way it works, right, and actually in this case, you don't even need scientific notation. I'll show that later. We'll be using that when I show scientific notation. But you can go straight across. You can go 2.54 times 0.0028, then divide it by the 0.015. If you hit times, it'll bring this up to the numerator, your calculator. It doesn't get that. So you don't want to hit times right here. The only way you can do that is if you put the entire denominator in parentheses. I tell students pretty much on all my calculations in the denominator, just put it in parentheses, make that a habit. Whatever's in the bottom, like the top, don't worry about it. Just go straight across, left to right. But once you get to the denominator and you hit that divide, the first thing you should do is just start using brackets or parentheses rather. And that's on that portion of the calculator. But your final answer should have 2 sig figs and it should be 11. What's funny is the easier operation is the more difficult for people in sig figs, because with multiplication division, you just count the number of sig figs, at least one, you're done. Here, we have to use precision. Remember what placement value on the measurement device determines how precise something is? I just tell people use placement value. So here I have 4.1 mils plus 3.75. If I punched in the calculator, I would get 7.85 mils. It's not milliliters. Yeah, mil is short for milli, and we'll get to prefixes next time, next lecture. But milliliter, because I'm adding, I don't square it, it stays. Goes back to what I said, you know, the x plus x is just 2x, there's no squared, okay? So because it's addition, it's just milliliters. It's additive. However, I want to go to the precision. So the 4.1, the precision, the last precision, as you see highlighted in red, is the tenths. And for the 3.75, it's the hundredths. So the least precise, the least placement value, tenths, is less than hundredths, right? The hundredths is more precise. You could even draw a line. The problem with drawing a line is you got to always align everything, right? So what I just say is just remember the precision, the placement value. So this number should go to the tenths, not the hundredths. So what do I do? 7.9. Now this upsets people, you know, but don't let it, okay? It's just how it is. So in this case, right, 14.82, 0.0291, if I was to look, this goes to the hundredths, this goes all the way to hundreds, thousands, 10,000s, which is least precise, the hundredths. So my answer should only go to the hundredths, not the 10,000s. I underlined it in red. So because I should only go to the hundredths, all right, the least precise, I look to the 9, I got to round up. It's 14.85 inches. Okay. B, I'm subtracting. This goes to the ones, this goes to the hundredths. The ones is less precise. I should only go to the ones. So just to avoid confusion, I'll erase that. So I go to the ones, not all the way to the hundredths. And I'm going to drop all this. That's an 8. So what do? Round up. I go here, right? This goes to the hundredths, the tenths, the ones. So where am I going to go? The ones. So I underline the ones. I'm going to drop this. It's greater than 5. I'm going to round up 257. And again, I'm using units, grams. Oh, and so really with all our calculations and measurements, there's 3 things you have to know. There's 3 things for all measurements, right? So all your measurements. There's 3 things. 1, the number. 2, the correct sig figs. And 3, not last, the unit. Need it. So D, I'm going to go to the tenths. It's the least precise. I underline it. It's a 2. I just drop it. Boom. Right? But again, because of the significant figure rules, I might need to use that scientific notation I showed earlier with the rounding, right? So typically with scientific notation, the first non-zero digit is where you place a decimal, and then you follow up with other significant figures or digits, right? The power, okay? So if the number, right? If the number is bigger than 1, then the power is going to be positive. If the number is less than 1, then the power is going to be negative. That's what you need to remember. Okay, if it's bigger than 1, positive exponent. Less than 1, negative. So we're moving the decimal to show placement value of 10. That's why we use base 10 for the power, because we could easily move the decimal base 10, right? So like in this example, 150 meters is the same as me saying 1.5 times 100. The 100 is basically 10 times 10, right? Because there's 2 zeros, so there's 2 10s. That's why it's 10 squared, because there's 2 10s. So it's 1.5 times 10 squared. Why is it positive? Well, this number is bigger than 1. So then my exponent is positive. Why is it a 2? You don't want to write 1.5 times 100 and then that's 10 times 10 to figure that out. You just go here where the decimal would be, because this is the ones place, and go over 1, 2. So it's move the decimal 2 times after the first non-zero digits. The number is bigger than 1, positive. Now in this case, right, how do we get this? It's like dividing it by, well, what placement is this? Tenths, hundreds, thousands, 10,000s, right? So when I move it to 7.5, really it should be 75 to 10,000s. But the way it's shown here, it's 7.5 over 1,000. It's kind of just showing you how it is. The easiest way to do it is I'm taking this decimal, I'm moving it behind the first non-zero digit. 1, 2, 3, right? So that's where they get the 7.5. And it's times 1,000s, because the 7 is in the thousands place, right? So when I do this division, I'm 1, 2, 3. So it's 10 to the negative 3, and it's negative because it's less. This number is smaller, right, than 1, right? 75 10,000ths is less than 1. So my exponent, when I put it in scientific notation, is negative. Why do we use scientific notation? Because we measure really big numbers in science, right? The distance to the next galaxy, right? Or the number of atoms, right? Because atoms are puny. In a liter, it's huge. Like nobody wants, that's tedious. You do not want to write that many zeros. So what do we use? Well, these are all trailing without a decimal, right? Because we're just using them for placement value. So they're not really significant digits, they're just placement. So we're going to we just have 3, and we're going to put the decimal right there. So after the first non-zero digit, there's 22 moves of the decimal to the left, and you get 3, 6, 9, 12, 15, 18. That's 21, and then one more, 22, 2.68. I drop all the trailing zeros without a decimal times 10 to the 22. Really big number, right? I don't want you writing out all those zeros. That's 21 zeros. Nah, scientific notation. Plus your calculator, it doesn't go, whichever calculator, it only goes to like 8 or 9. So it's going to put it in scientific notation for you. We also deal with really small numbers. So, we're going to do all those zeros? Nah. Again, what am I doing? I'm moving this over. 1, 2, 3, 4, 5, 6, 7. Right? So I moved it over 7 to get behind the 1, the first non-zero digit. Right? I'm dropping those zeros because they're leading. They don't count. I'm including this 0, though, because it's trailing and there's a decimal. It's 1.40, because that trailing 0 is significant, times 10 to the negative 7. Why is this a negative exponent? Because this number is much smaller than 1. So again, with rounding, here I have 3 sig figs, here I have 2. If you were to do this on your calculator, here's a little practice. You would hit 5.44, and to get the times to the 10 to the 7, if there's an EXP button, So some calculators actually have EXP buttons. Let's see, does mine have it? No, I have different calculators because I like to try to show people. This one doesn't even have an EXP button. It just has, it's not gonna, it has a number, it just has right here, 10 to the X. So it actually puts it in scientific notation just by hitting that number. Some have EXP. In this case, we have an EE, right? But to get it, you actually have to hit 5.44, and then you would actually have to hit the second function button, the blue button on the upper part right there, and then hit that EE, which is above the X to the -1 on your calc. Then you'd hit 7, then you would hit divide, 8.1, second function EE, 4, and then you would hit equal. Sorry, my computer's about to die here. And I get this really big number, right? How many sig figs should I have? 2 or 3? I should have 2. So 1, 2, this is a 1, I drop the rest, 670 grams per mole. So scientific notation, 2.4 times 10 to the 6, 2.56 times 10 to the -3, 0.00007 kilometers, right? So this is getting some practice. All right, move this over. How many? 1, 2, 3, 4, boom, millimeters. So these are examples, but on your sheet, we got to go, right? We're going to do this. So I need to put these in scientific notation. All of these are significant. So I got to write them all. We're going over 1, 2, 3, 4. So the exponent's 4. It's positive because this number is bigger than 1. So it's 4.2784 times 10 to the 4 centimeters. Okay, now here, I want to go after the first non-zero digit. And believe it or not, I got to write all this because these are captive. They count. Trailing count because there's a decimal. Leading don't. But how many do I move it over? 1, 2, 3, 4. So it's 2.00. I know you're going to hate me. 500 times 10 to the -4. Why negative? Because it's less than 1 feet. We go over here. B. Oh, I'm supposed to go down. Sorry. We go B right here on exercise 5. And I'm going over 1, 2. This is an easy one. 1.2 times 10 to the 2 miles. And that's because it's bigger. So over here, why did I do this? It's because this stuff comes up. I pick numbers that come up. 1, 2, 3. So it's 9.842010. Why am I counting? Captive, trailing with a decimal, times 10 to the 3 kilograms. Over here, 1, 2, 8.19 times 10 to the -2. Why negative? Less than 1 seconds. Over here, oh, there's a decimal. That means these trailing count. I can't just drop them like I did with the 120. So I'm going to go 4.300. I moved it 1, 2, 3 times 10 to the 3 pounds. By the way, I would never have you put that in scientific notation for numbers like this. Okay, like I wouldn't ask you to put it in scientific notation. I'm just showing you if you have to how to do it. Okay, if you can express the number with the correct number of significant figures without scientific notation, and it's a small number, then do it. Okay. This is 4 sig figs because these are trailing after a decimal. I'm moving it over. 8.600 times 10 to the +1 because it's greater than 0 degrees Celsius. This, I'm moving it over 1. So it's 5.5392 times 10 to the Why is it negative? It's less than 1, -1 milliseconds. So now we're doing the opposite. Exercise 6. We're taking this and we're putting it in standard form, okay? Again, I typically don't ask you to do this. This is just so you're comfortable. If you have to, because significant figures, you'll be okay. This is positive. So what am I doing? I'm making this number bigger. How do I make it bigger? 1, 2. 539.0 liters. Why do I incorporate the 0? Because it's trailing with the decimal. -5. That means I got to make this number less than 1. How do I do that? I got to move it 1. Ooh. So it's going to have, this moves it over 1, and I need 4 leading zeros. 1, 2, 3, 4, 5 meters squared. And you could redo it, 1, 2, 3, 4, 5. So I'm going to move this over 2. Boom, boom. 1277.8. Ah, there's a 0. It's trailing. Put that. Feet. Move this over 1, 2, 3. 0.00603 grams. Move this over 1, 2. 0.025. Those are trailing zeros after decimal. Wow, that's a really degrees Fahrenheit. Okay. There you go. That's cold. That's cold. And precise. Going over here, 10 to the 3. 1, 2, 3. 1883. They're trailing zeros. 0.200 hours. Again, I went through that fast just because it's getting to be kind of long lecture here. So, and it's perfect. That's like your first full-on lecture of basically an hour and 25 minutes. So I'm going to go ahead and stop the recording. And at that point, you guys can continue on to the next lecture if you like, take a break. As always, during my lectures, you can pause, come back. I'm just going to do them in about 1 hour, 25-minute blocks. This lecture was introducing you to chem, the scientific method, the math review, significant figures, rounding, and calculations. The next lecture to follow in chapter 2, we'll continue with our measurements. We'll talk about the metric system, the English system, converting in each of those and between those, and then performing complex word problem solving. So thanks for your patience. Really enjoyed it. Even though you're not here, I appreciate it. So thanks for watching.